Alright, hello again everyone and welcome to this proof breakdown of the central limit theorem, here on referred to as the CLT. It is one of the fundamental results in probability and statistics, and if you want to know why some sports teams tend to be predictable over an entire season despite individual game fluctuations, or why trends appear over large groups of people despite individuals being amazingly unique, then the CLT is a central theorem to know. So future mathematicians, statisticians, logicians, and even chaoticians, let's sit back and take a moment to walk through exactly why and when its insight holds. Today, we will discuss the normalized sum version, but the insights of this theorem holds true for the normalized mean as well. The proofs are direct, derivable using common mathematical techniques, and draw upon knowledge from other disciplines like real, functional, and Fourier analysis, amongst others. We'll be going over three versions of the proof, the first one being the moment generating function version of the proof, then the cumulant generating function version, and finally the characteristic function version. Each methodology has different benefits as well as weaknesses. For example, the moment generating functions is a much more introductory proof that is a bit more straightforward and often covered in undergraduate statistics and probability courses. However, it has a weakness in that it produces moments that are intertwined with their predecessors, making these moments harder to interpret individually as well as asymptotically. The cumulant generating function addresses this issue by taking advantage of a log transformation of the moment generating function. This transformation allows for the cumulants to represent individual characteristics of distributions, making them much easier to analyze asymptotically. However, these two methods have one shared weakness in that they assume that moments and cumulants of random variables and corresponding distributions are well defined, which is not always the case. In that situation, we have the characteristic function version of the proof, which is always available to us and can handle situations where a random variable or its distribution are not well behaved. To briefly recall what the central limit theorem insight is, it states that the normalized sum of independent random variables tends to a normal distribution even if the original variables are not normally distributed themselves, which is a counterintuitive result. However, we are going to rigorously prove that this is the situation across the board. Now, since the moment generating function version of the proof is so well covered and accessible, we are simply going to do a quick recap of the steps involved without actually stepping through the derivations themselves. If you are looking for that kind of walkthrough, specifically for the moment generating function, I encourage you to look up some of the MIT OpenCourseWare offerings that cover stats and probability, as they will likely have the detailed walkthrough of the moment generating function proof you seek. Okay, so here is the quick recap of this MGF version of the proof. We start off with the moment generating function definition as the expectation of the exponent to the txth power, where x is your random variable. We assume that the moments exist across the board. We then use the moment generating function properties on a sum of random variables to create a product of their individual moments, independent random variables. The two properties of note are known as convolution and scaling, where the former states that the moment generating function of the sum of independent random variables is equal to the product of their individual moment generating functions. If we want the MGF of a random variable times a constant, we have the scaling property that states that the moment generating function of a random variable x multiplied by some constant is equal to the moment generating function of that random variable of the constant times t. We then normalize the sum of those random variables in the resulting product, then approximate the moment generating function using a Taylor series expansion, then use the fact that at the limit, 1 plus x over n all to the nth power is approximated as e to the xth power for a small x and large n. Then we take the limit to arrive at the limiting distribution, which is that of a normal distribution, and we know it's normal by the uniqueness property of distributions. As mentioned earlier, moment generating functions have some weaknesses. We may want to see the moments independent of one another, which moment generating functions do not allow. However, cumulants represent distributional contributions in a way that separates them from dependencies on lower order characteristics, making them easier to analyze asymptotically. Given our original moment generating function was exponential, perhaps a logarithmic transformation could do something for us. Specifically, given the functional properties of e to the x and log x, it can be advantageous to transform the product of moments, as seen in the moment generating function, into a summation of cumulants, which will be detailed momentarily, using the cumulant generating function. Alright then, let's see how that works with our first detailed CLT proof using the cumulant generating function we recently defined. Okay. Let's go ahead and start with the cumulant generating function definition and assume cumulants are well defined. And just as a reminder, our moment generating function is equal to the expectation of e to the txth power. Then, using the general Taylor expansion of e to the x to expand our e to the tx, we have the following. We'll now apply the expectation operator and its linearity property to come to the approximation of our moment generating function. But notice that the above form can be rewritten as big 1 plus big O of t, where the big O of t is the tail of our moment generating function Taylor expansion. So now we take the log of that MGF equation to get our cumulant generating function. Luckily, we have a technique to do so conveniently. Quickly recall that the Taylor series expansion of a function of form log 1 plus t is the following. And generally speaking, as the summation from n equals 1 to infinity of negative 1 to n minus 1 times t to the n over n. Using that approximation, we expand the cumulant generating function as a power series like so. Notice that after our expansion and rearrangement, our coefficients look exactly what we expect our mean, variance, and other orders to look like. So for example, our variance looks exactly as we expected, which would equal the expectation of the squared random variable minus the expectation of that random variable squared. These coefficients are referred to as cumulants. Note, we can systematically recover these cumulants by taking successive derivatives about 0 of our cumulant generating function. So let's do a quick exercise to demonstrate this in a way similar to how we recover raw moments of the moment generating function. So the 0th cumulant is 0 at t equals 0. Our first cumulant at the first derivative at t equals 0 is just our mean. And then finally, our second cumulant at the second derivative at t equals 0 is our variance, as you'll see here. And we would continue taking successive derivatives about t, or with respect to t, in order to get the remaining cumulants. Quick aside, this last cumulant is particularly interesting as it demonstrates how cumulants represent a specific distributional character, unlike raw moments of a moment generating function. But we're going to hold off on diving into the details of that until later. For now, let's continue on our train of thought. So with this separability, we want to see how each cumulant behaves at the limit. To do so, we need to briefly cover cumulant properties analogous to that found in moment generating function properties. The first property being the convolutional property that states that the cumulant generating function of the sum of two independent random variables is the sum of their individual cumulant generating functions. This is going to be crucial when we analyze the cumulant contributions to a cumulant generating function at the limit. The second property that's important to us is scaling, which states that the cumulant generating function of a random variable multiplied by some constant is just the cumulant generating function of that random variable evaluated at the product of that constant and t. So, now given n random zero mean variables and using the two previously mentioned properties, we have the cumulant generating function of their normalized sum as the following. But we want to convert this into cumulant terms, and for that we need to manipulate the cumulant generating function of that normalized sum in a way that focuses on cumulants of each random variable individually. Also, note that for any zero mean random variable, its cumulant generating function is the sum of the product of t to the mth power and the ratio of the sum of cumulants for that random variable and m factorial. Substituting our scaling factor turns our t to the mth power to t over the square root of n and that whole ratio to the mth power. Then the sum of n independent zero mean random variables is as follows. To understand each cumulant's behavior, we focus on the coefficient of each t to the mth power over m factorial. To do so, we first isolate the coefficients by order over independent random variables, giving the following. Notice that the summations here have switched, as we are now summing over each cumulant of each random variable in our normalized sum, rather than the cumulant generating function of each random variable. Then, extracting the coefficients gives us the mth cumulant of the normalized sum in terms of the mth cumulants of each addend. Notice when cumulants are bounded though, higher order cumulants go to 0 when m is greater than 2, so those moments contribute nothing to this cumulant generating function. This is our first hint that we're facing our normal distribution. By our previous formula and the independence of our random variables xi, we have that the nth order cumulant of the normalized sum is equivalent to the nth cumulant of our n random variables. So that when m equals 1, we have the first cumulant of the normalized sum is 0, due to our zero mean random variables assumption. Then when m equals 2, we have the second order cumulant is just the variance. Finally, any order greater than 2 goes to 0 as previously established. Then, given the above, and knowing the first and second cumulant survive, our limiting cumulant generating function of the normalized sum is the following. That form above is exactly the form we know of a normal random variable with zero mean. This reconciles with the same outcome using moment-generating functions using a zero mean parameter. However, as an exercise for comparison, we're going to go ahead and calculate the cumulant generating function of a generic normal random variable with zero mean to confirm our findings. To do so, we take the moment-generating function of a normal random variable with zero mean, take the log of that to get the cumulant generating function, and then see what the resulting general form is. But notice that with our zero mean random variable assumption, the only add-in in our cumulant generating function left over is sigma squared over 2 t squared, which matches the exact same limiting cumulant generating function form that we just derived previously. Alternatively, recall the closure under linear combinations of normal random variables, which states that the sum of normal random variables is itself a normal distribution. Again, with our zero mean starting assumption, we have that the normalized sum, in this case, approaches a normal distribution with its associated variance. So given A and B, we are confident our normalized sum is itself normal with zero mean at the limit due to the uniqueness property of distributions. Done. So why use cumulant generating functions? Well, first, cumulant generating functions add amongst random variable collections, whereas moment generating functions multiply amongst random variable collections. Cumulant generating functions also explicitly ID cumulants, which are contributions to a random variable's distribution independent of one another. This allows us to see higher cumulants completely disappear at the limit. Finally, moment generating function moments are interdependent and harder to interpret because they use raw moments. Say, for example, the raw moment of the expectation of x squared. We know from definition that this is equal to the variance of x plus the square of the expectation of x, which naturally demonstrates that the raw moments are interdependent of one another. In this case, the second raw moment is dependent on the first raw moment. But distribution-related analysis using cumulant generating functions and moment generating functions assume all moments are well defined. But we know of distributions where that's not the case, like the Cauchy, aka Lorentzian distribution. Its tails are too heavy, and when we consider the integration properties of raw moments, we can see that the integral does not converge for Cauchy random variables. To elaborate, the nth raw moment is defined as the improper integral from negative infinity to infinity of x to the n multiplied by the product of the PDF of x dx. Substituting the Cauchy PDF, we see that its decay rate is not fast enough to offset the polynomial growth of x to the n. As a result, the raw moments of the Cauchy distribution do not exist for any n greater than or equal to 1, and the moment generating function is also not well defined as it does not converge. So, what do we do? Well, someone thought that same question and sought techniques to corral potential divergence. The technique they used was the Fourier transform. Since complex exponentials include oscillatory behavior, the Fourier transform helps express probability distributions even when raw moments do not exist. For our purposes, the characteristic function is the Fourier transform of a PDF of our random variable. This Fourier transform converts a distribution into bounded frequency domains, and the transformation always exists. Additionally, it allows us to avoid log transformations as well. It encodes all information about x's distribution, meaning we can recover the PDF from its characteristic function using the inverse Fourier transform. This also provides a unique one-to-one mapping between the two forms, which explains the naming of this function as characteristic. Okay, let's go ahead and dive into the third and final CLT proof, using these characteristic functions as well as the properties of the imaginary conversion. So first, let's start off with the characteristic function definition, which is an imaginary transformation of the probability density function of our random variable. So, our characteristic function for any random variable is equal to the expectation of e raised to the I txth power. Okay. Then we expand the characteristic function of a single random variable using the Taylor series method we've been using for every single proof so far. Then we'll reformulate the characteristic function of a sum of random variables as a product of characteristic functions of each random variable. Then substitute equation 3 into the previous result, normalize the sum, and then use an exponential approximation of form 1 plus x over n, all raised to the nth power. Then, using that approximation, we can see that we recover the known characteristic function of a normal distribution. But notice, we've only proven pointwise convergence. We need a distributional convergence argument in order to make our point. Luckily, we have such a theorem to help us bridge that gap called Levi's convergence theory or continuity theorem. This states, if the sequence of characteristic functions converges pointwise to some function which is itself the characteristic function of a random variable, then the sequence converges in distribution to that random variable. So then, by leveraging Levi's convergence theorem, we can now claim that the normalized sum of n independent random variables is approximated by a normal curve about mu, which in this case is 0, and variance, or sigma squared. Done. Okay, that's 3 ways to prove the central limit theorem. We use moment generating functions, cumulant generating functions, and finally characteristic functions. Each proof methodology has its benefits. For example, moment generating functions are typically the most straightforward proof method, and they are often covered in undergraduate courses in statistics and probability. Cumulant generating functions are a bit more advanced, and they're often covered in graduate level courses or upper division undergraduate courses. They also have the benefit of separating distribution characteristics apart from one another so that they're much easier to interpret, unlike the moment generating functions. But these two previous methodologies rely on the assumption that the moments are well behaved. In the case they are not, we have the characteristic function methodology, which is always available to us, and has the benefit of mapping characteristic functions to their random variables and distributions in a one-to-one fashion. The standard central limit theorem is a powerful result, but it has many extensions. Specifically in our presentation, our pedagogical CLT proofs, which were of the basic form, required independent random variables, but there are many more circumstances beyond that in the real world. Think about independent but differently distributed measurements from multiple sensors. We need something a bit more robust and in general in that case. Or what if we wanted to actually characterize the rate of convergence with IID random variables? Or what if we wanted to know the behavior of an entire sequence of partial sums of IID random variables? In such cases, the standard CLT, as presented, may not be sufficient on its own. Luckily, capable and thoughtful minds have addressed these exact questions. Specifically, Lindbergh-Feller's CLT provided necessary and sufficient conditions for the CLT in the presence of independent but not necessarily identically distributed random variables, assuming Feller's condition holds. Barry-Yassine's theorem gives us an upper bound on the error in normal approximation, providing a quantitative rate of convergence for CLT. And finally, Donsker's invariance principle demonstrates that a normalized process of partial sums of IID random variables converges to a Brownian motion. All three and more provide greater insight into the CLT behavior, but I leave those as an exercise for you to explore further. The central limit theorem is more than just a theoretical result, though. It explains why polling works, why casinos profit in the long run, and why large data sets exhibit predictable behavior. The more you study it, the more you'll recognize its fingerprints in the world around you. With that said, I hope you found this discussion insightful. If you have any questions or feedback, feel free to leave a comment, and I'll get back to you as soon as I can. If you enjoyed this tutorial, consider leaving a like so that the YouTube algorithm can help other learners find this content. Otherwise, I appreciate the time you took to explore this topic with me today and hope you have a great day. Take care.